Right, students? So, day 10 is written, actually day 10 plus 1 it is. What it is then? Thermodynamics we were studying yesterday. Yesterday we discussed about 0th law of thermodynamics, which talks about thermal equilibrium. Now, first law of thermodynamics. Okay, the first law of thermodynamics is the main thing as far as thermodynamics is concerned. Okay, so what it says that it gives a relation between how much heat we are giving, how much change in internal energy is coming, and how much work is done. Internal energy basically means what? Internal energy in case of ideal gas is basically change in kinetic energy of the molecules of ideal gas. Okay, change in internal energy or internal energy as such. We represent this with U. And I am saying what? U is what? Kinetic energy. Kinetic energy of molecules of ideal gas. Right? And kinetic energy of molecules directly depends on temperature. Directly proportional to temperature. Okay. So that means U is a function of temperature. More the temperature, more is the internal energy of the gas. Less the temperature, less is the internal energy of the gas. So first law of thermodynamics, if we come back, so first law of thermodynamics says that if you are going to give, let's say, delta Q amount of heat to the system means gas, that delta Q first is going to increase the internal energy of the gas. Obviously, when you are going to give heat to the gas, temperature will increase. And then what it will happen? Then it will expand. Okay, so when it will expand, then it will do some work. So first, whatever heat you are giving, it increases the internal energy of the gas, and then it's going to do the useful work over it. Okay, that is our first law of thermodynamics, right? Nothing new in that, we were knowing it, but this is important. Now, what we have seen when we were discussing about work done, okay, when expansion happens, work done is positive, that is work done by the gas. When compression happens, work done is negative. Remember that. Okay. So let's do a few questions based on this. Two questions I have written over here. Simple questions. Delta Q, that means heat given, is 100 joule. Initial internal energy is 50 joule. Work done positive 20. Is asking what is the final internal energy. Okay, simple question it is. So we know that first law of thermodynamics is delta Q equal to delta U plus W. Further, delta Q equal to U final minus U initial plus W. Okay, delta Q is what? 100. UF is asking, UI is 50 and W is 20. Okay, so what we have now? This is 50 over here, so minus 50 plus 20 is minus 30, minus 30 will come this side. So U final is equal to 130. U final equal to 130 joule. Simple question, right? Second question also is there, similar. What is that? Delta Q is minus 20, UI given again, W given, UF is asking. Same question in fact. Okay, so we'll solve in the same way. Delta Q equal to delta U plus W. Delta Q minus 20, UF minus UI plus W. So minus 20, UF we are finding. What is UI? 40. So minus 40. And work done is negative. Work done is negative means what? Compression. Compression is happening. Work is done on the system. Okay, so minus 10. This is 40. This is minus 10. So this is minus 50. Minus 50 will come this side. There will be plus 50. Plus 50 minus 20. So UF value is coming 30 joule. UF value is coming 30 joule. Simple question. Like these questions also will be there in NEET. Yeah, it will be there, but they will not write it that easy. They'll write a statement and we have to get this value from that. I have written it like this to save our time of the class. Okay. Alright, now what we have? Thermodynamic processes. What processes we are going to have? Mainly we talk about 5 processes. What 5 processes? The first one is isochoric process, isochoric or constant volume process. Constant volume process. Now, since it's constant volume, that means change in volume is not there. Change in volume is not there means work is not done. Delta V 0, W 0. That means delta Q is equal to delta U. Delta Q equal to delta U. So, if suppose Q is given, that means heat is given, Q is added, what will happen then? Internal energy of the gas will go up. Internal energy will increase. Okay, then temperature also will increase. Why? Because U is a function of temperature. U increases means temperature increases. Okay, fine. What about pressure then? Now it's a constant volume process. So constant volume process means P is directly proportional to temperature. Constant volume means P is directly proportional to temperature. If temperature goes up, means pressure also goes up. Now these are the things that can be asked from you directly. In a constant volume process, heat is added, what will happen to pressure? Okay, so this is the way. And suppose that if heat is taken, heat is released, okay, that also we'll see. Okay, Q is released. So when Q is released, heat you are taking from the system, U goes down. U goes down means temperature goes down, temperature goes down means pressure goes down. This is constant volume. Okay, now in the same way, let's talk about isothermal process. Isothermal means constant temperature. Okay, let's see. The second one, constant temperature or isothermal. Isothermal process. Okay, now in isothermal process, what we have? T is constant. Delta T is 0. Okay, so if delta T is 0 means change in internal energy is 0. Why? Because T is not changing, U is a function of T. So delta T 0 means delta U 0. So delta U 0. Okay. So now what we have to see? If Q is added, what is going to happen? Okay. So if Q is added, we said T is constant, T is not changing. Q is added, then what will happen? Work will be done. First law of thermodynamics, delta Q equal to delta U plus W. Delta U 0 means delta Q equal to W. Work is done. Q is added means work is done by the gas. Okay, so work is done. Now when you do the work, positive work, volume increases, right? Okay, so when Q is added, volume increases. Volume increases, pressure decreases. How? Because in isothermal process, P is inversely proportional to V. P is inversely proportional to V in isothermal process. So if V increases, P decreases. Right, T is constant anyhow. So this is isothermal. Then let's talk about isobaric. Isobaric process. That means constant pressure. Okay, pressure is constant now. Okay, so here is pressure constant. Then what we can say about this now? So if pressure is constant and we are going to give heat, okay, Q is added. Then what happens? When you are adding the Q, delta U increases. Because in this one temperature is not constant. So when you add heat, Obviously, gas will absorb the heat. So U increases. Q is added, then U increases, not delta U. U increases. If U increases means temperature increases, no doubt about that. U increased, temperature increased. Okay, then what will happen? Expansion will happen. We have added Q. Expansion will happen means V will increase. What about pressure? Pressure is constant. Okay, same way if Q is removed, Q is released. What will happen? U will go down, temperature will go down, volume will also go down. Okay, so this is isobaric process. Now same way one more process is there that we will see. Okay, what is that? Adiabatic. Let's see adiabatic also. Adiabatic process. These are all important things that I am telling you. Okay, very important. You should know them. Adiabatic process. Adiabatic process is what? No heat transfer between surrounding and the system. There is no heat transfer is done. Okay. Delta Q 0. So if delta Q is 0, according to first law, what is first law? Delta Q equal to delta U plus W. Delta Q is 0. It means delta U equal to minus W or W equal to minus delta U. What is the meaning of that? Since no heat is given, if suppose positive work is done by the gas, that means expansion is happening, then internal energy is going to decrease. That means temperature will go down. Okay, but if suppose that negative work is done, that means work is done on the system, you are compressing. So when you are compressing the gas, internal energy increases. That will be positive. Temperature will increase. Okay, so in this case, suppose we are talking about this here. Now what is this? Minus W. Minus W means compression. Minus W means compression means I already told you that V is decreasing. Okay, so volume is going down. Okay, delta U is positive, increasing. So delta U is increasing means temperature is going up. Temperature is going up. And since it's, what we are doing here? Compression. So can we talk about pressure also? Temperature has increased, volume has gone down. So volume is going down means pressure is increasing. Pressure is also increasing. Now how can I say? See, in isothermal I say P is inversely proportional to V. Here also similar relation is there. Which one? Say P is inversely proportional to V to the power gamma. Okay, adiabatic process means PV to the power gamma equal to constant. Isothermal means PV is constant, right? Here we have written. So this is PV to the power gamma is constant. So if volume is going to decrease, then pressure obviously is going to increase. So this relation is there during compression. But if suppose I want that expansion should be there, so in expansion what will happen? Now as I say expansion means volume is increasing. Okay, volume is increasing. Volume increases in adiabatic process, that means temperature will go down. Minus is here, you can see. Okay, so temperature goes down. Temperature goes down, volume is increasing, means pressure will go down. Because inverse relation is there. So this information you should have, you should be able to take out from the process itself. Okay, there will be questions like this on this, right? Okay, let's move ahead. Now one more process is there that I should discuss, that is cyclic process. Let's see, in the next slide can we discuss? Yeah, it's there, cyclic process is written. The cyclic process means is what? You are returning back to your initial state. What is initial state? In thermodynamics, any state is represented through pressure, volume and temperature. Its coordinates are pressure, volume and temperature. Like normally in mathematics when we do, the coordinates we take as x coordinates, y coordinates, z coordinate. But in thermodynamics, our coordinates are pressure, volume and temperature. So if gas returns back to initial state, means initial pressure, volume and temperature. Initial pressure, volume and temperature. Then process is cyclic. Right. So if it is a cyclic process and we are saying that whatever was initial temperature, final temperature is also same, then change in internal energy in cyclic process will become zero, right? So delta U in cyclic process is zero. So if this is zero, then we can write first law as delta Q equal to work done only. Delta Q equal to work done. Correct. So if it is added, then work is done. If it is taken, work is done on the system. Okay. So if suppose the same way we write, what are we going to write? If Q is added, Q is added. Now Q is added, then we said delta U is zero in entire process. That means work will be done. Who is doing work? Gas is doing work. Gas is doing work means volume is going to increase. So Q is added means some work is done. But we said that it's going back to the initial process, initial condition. So final volume and initial volume also will be same only. There's no doubt about that. But there will be different processes in that will be done. Okay. So expansion must have happened. Okay. Expansion must have happened. So we can say like that. Okay. We'll understand that. This will come back when we'll study cyclic process again. Then we'll discuss. At the moment, it will be tough here right now because we are talking about theoretical aspects. Okay. So cyclic process, what we understand at the moment, delta U cyclic is 0 and delta Q equal to W. Fine. Then there is something written as state function and path function. Okay. What is state function? Actually, internal energy is a state function. Internal energy is state function. Or you say change in internal energy is state function. Okay. Delta U. Here I write change. Change in internal energy is state function. That means it depends on initial and final conditions only. It depends on initial and final condition of the gas. How it reach in those initial and final conditions, it doesn't depend on that. Only initial and final condition. Like potential energy used to be there. Potential energy was what? It depends on your initial position and final position. Okay, if your final position is height 10 meter and initial position is on ground, so we'll write mg into 10 minus 0. Change in potential energy. Right. How you went to a 10 meter height, okay, it doesn't make any difference. Exactly same way. Change in internal energy also depends on initial and final condition only. How you reached, it has nothing to do with that. Okay, and which particular variable it depends on? Temperature. So it depends on difference of initial and final temperature only. Delta U depends on initial and final temperature only. How you reach there, it doesn't depend on that. Okay, so change in internal energy is state function. Path function, work done is a path function. Okay, work done is path function. That's why work done in all the processes will be different. Adiabatic different, isothermal different, constant pressure different, constant volume different. Because they will all be going through different paths, and work done also will be different. So work done is path function. Delta Q is also path function. Can we say like that? Delta Q is also path function. Is it different for different processes? Answer is yes. Delta Q is also different for different processes. Okay. So yes, at times we can say, but delta Q equal to delta U plus W, right? But still, it does depends on path. For every path, there is a different value of delta Q as well. Okay. So you should know what is state function and what is path function. Okay. All right. Let's see again. Some numericals are there. 20 joule of work is done by surrounding isothermally. Isothermally is given. What changes will arise in system? Okay, fine. So isothermally is there means delta T0 first. Delta T0 means delta U is also 0. You are giving Q. Q is 20 joule. Okay. 20 joule of work is done by surrounding isothermal. On surrounding or by surrounding? If you are giving 20 joule, okay, work done itself is 20 joule, not heat given. So 20 joule of work is done by surrounding. Now when surrounding does the work on the system, that means it has to be compression. Okay, surrounding is working. Surrounding means external thing is working. The external thing will, how it will work? It will compress only. When the gas works, it expands. So work done is given to you as minus 20. Okay, fine. What question is asking? What changes will arise? What changes will arise? First of all, if work done is minus 20, that means Q is equal to delta U plus W. Okay, this is 0 and this is minus 20. So that means Q is minus 20 joule. That means heat is released. Heat is released to the system. Minus means heat is released. Plus means heat is added into the system. So minus 20 is heat released. Okay. Now what happened? When we are saying W equal to minus 20, that means volume has decreased. So you have decreased the volume. Volume has gone down. And if volume has gone down, I can say pressure has increased. So pressure has gone up. These are the changes. Okay. These changes are going to come in the system. Okay. Then what else we can say here? Let's see what the next question is. If minus 20 joule is added in a system in isochoric process, how will process change? How will pressure change? Not process. Okay, let's see. Isochoric means delta V is 0. Constant volume. That means work done is 0. Okay. Then minus 20 joule is heat added. So Q is minus 20. So Q is minus 20. That means according to first law, delta U will be minus 20 because work done is 0. Okay. Delta U is minus 20. So when we say delta U is minus 20, that means UF is less than UI. If UF is less than UI means temperature has gone down because internal energy is a function of temperature after all. Okay. So temperature is going down. Okay. Now temperature has gone down and it's a constant volume process. Isochoric means constant volume. And constant volume process means pressure is directly proportional to temperature. Constant volume means pressure directly proportional to temperature. So if temperature is going down, pressure is also going down. Okay. So this is how pressure changes. Pressure is going down. Okay. The temperature is going down, pressure is going down. Fine. Next, which process is slow or fast in nature? Nature. Okay. So we will say that adiabatic process is fast. Adiabatic process is fast and isothermal is slow. Isothermal is slow. Isothermal process is slow. Now, we have to give the example also then. How can we say adiabatic is fast in nature? So, what are the examples of adiabatic process? Bursting of tire. Bursting of tire means how it will happen? Suddenly tire of cycle or any vehicle will burst. And what will happen because of that? Sudden expansion happens of the air which is there in the tire. Sudden expansion happens because internally in the tire a lot of pressure is there. And when it bursts, it will go to atmospheric pressure. Pressure suddenly decreases from that much high pressure to atmospheric. So expansion happens suddenly. This is adiabatic process. And if you go there and touch the tire, you will find it's very cool. Okay, so temperature has gone down. It's adiabatic process because expansion has happened. So bursting of tire, instantaneous process. In nature, this is the example of adiabatic. Now in nature, what is the example of isothermal process? Conversion of ice into water. At what temperature ice converts into water? 0 degree centigrade. Process is fast or slow? Slow. Same way, conversion of water into steam. Where it happens? At 100 degree centigrade. Process is fast or slow? Process is slow. Okay. Nature I am saying, I am not saying through geyser. Geyser is not nature. Okay. So, conversion of ice into water at 0 degree centigrade. A slow process. So we say that isothermal process is slow and adiabatic process used to be faster. Okay. Alright. Then, okay. Now we have specific heat. Specific heat is what? We know the definition already. The amount of heat required to raise the temperature of unit mole of gas by unit degree centigrade. It's called specific heat. C, we represent this with C. Amount of heat required to raise the temperature of unit mole of gas by unit degree centigrade. So delta Q is actually written as NC delta T. Fine. But we are more concerned with specific heat at constant pressure and specific heat at constant volume. Okay. So specific heat at constant volume. And specific heat at constant volume we write as CV. Definition is what? Same definition. Only the process is constant volume, but specific definition is same only. Delta Q equal to N delta T. Okay, so at constant volume, heat given delta Q is actually equal to NCV delta T. Okay, at constant volume, heat given is NCV delta T. If you give heat, it's going to increase the temperature. Okay, and it is written like this. Okay, fine. At constant pressure then, specific heat at constant pressure. Now that we write as Cp. This is Cp. Here that is exactly same, no change. What is going to come in this case? This is constant volume, this is constant pressure, remember, at constant pressure. This will be written as NCP delta T. Delta Q equal to NCP delta T. Okay. Further what you can do? Okay. We'll try to see something over there. So this is constant pressure, this is at constant volume. Now if constant volume if we talk about, we know that at constant volume work done is 0. Okay. So delta Q equal to delta U, where at constant volume, isochoric. Isochoric process, we know that delta Q equal to delta U. So delta Q is what? CV delta T. So delta U is NCV delta T. So okay, fine. No problem in that. Okay. At constant pressure then, at constant pressure, delta Q is equal to delta U plus W. Okay, constant pressure. Delta Q is what? NCP delta T. That's what we saw. If change in temperature is delta T, then change in internal energy will be NCV delta T only. Why? Because internal energy is function of temperature. It's not going to change. Here also if delta T change was there, okay, change in internal energy was NCV delta T. And here also if change in temperature is delta T, change in internal energy here also will be NCV delta T only. Because internal energy is state function, and state function depends on which variable? Temperature alone. Doesn't depend on pressure, doesn't depend on volume. Who? Internal energy. It only depends on temperature. So if temperature change here is this, and here also same temperature, then change in internal energy here and here will be same. For all the processes it is same. That's what we said. It's a state function. It is not a path function. It is not a process function. Change in internal energy is not a process function. It will be same for all the processes. If change in temperature is same in all the processes, the value of change in internal energy will be same in all the processes. Okay. So NCP delta T equal to NCV delta T plus work done. Plus work done. Now what is work done here? Now work done, as we studied in fluids, when we talk about fluid, work done is actually pressure into change in volume, P delta V. Or PdV if pressure is variable. Okay, so what's going to come here? If you are going to write P delta V in this one, because I need a relation here. So P delta V, what we can write? We know that ideal gas equation is PV equal to nRT. Okay, if I am going to differentiate that ideal gas equation with respect to temperature, okay, so differentiate. Pressure is constant, remember, okay. So if you differentiate with respect to temperature, pressure is constant, just leave it. This is dV by dt. nR is anyhow constant. Differentiation of T will be 1. Okay. So P dV you can write as nR dt. So in place of this P dV we can write as nR dt. So work done will become nR dt, or in this case we are writing delta T because delta T is the temperature change. So we will write nR delta T. So what is going to come? Let's see. Okay. So this particular function will be writing as NCP delta T equal to NCV delta T plus nR delta T. Okay, so N delta T, N delta T, N delta T cancel. So what we are getting? Cp equal to Cv plus R. That means Cp minus Cv equal to R. Cp minus Cv equal to R. I think it's not visible to you. Just a moment. Cp minus Cv equal to R is not visible, right? Just a moment. Okay, and bottom is also not visible to you of the board. Here it is. Okay, so Cp minus Cv equal to R. Now Cp minus Cv equal to R, is it for only for constant pressure process? No, all the processes. Cp minus Cv equal to R, this relation is used for all the processes. It is not dependent on any particular process. Okay. We know that, right? Cp minus Cv equal to R is very important, and this is called as what Mayer's relation also. And what Mayer's relation says? Mayer's relation says that for a same change in temperature, in constant pressure processes, more amount of heat is required as compared to constant volume process. Okay, why? Because in constant pressure process, work is also done. You give the heat, Suppose 10 joule you have given the heat, okay, 10 joule is taken by the gas, correct, but what happened is it started doing work, so it does 4 joule of work. Now change in internal energy is what? 6 joule only, correct. Now for 6 joule change in internal energy, if I am going to give the heat in constant volume process, how much heat I have to give? 6 joule only, because work done is 0. So in constant pressure process, how much we did? Gave the heat 10 joule. In constant volume process, how much heat we gave? 6 joule. Okay, for same change in temperature of the gas. So Mayer's relation says that at constant pressure, more amount of heat is required, or more amount of heat is to be given for the same change in temperature in comparison to constant volume process. This is the relation. Okay, now this relation is per mole. R is what? Universal gas constant. So it is per mole. That's very important. Sometimes the question will be asked in which they will be giving you the masses. Masses will be given 2 gram, 3 gram and all that. Convert it into mole, then only apply this relation. Okay, let's see if it's possible. We'll take a question or two like that. Right. So this question, but before this question, let's discuss about let's go, where is the vacant one? Empty slide. Okay, here it is. So Cp minus Cv equal to R we got. Okay, but at the same time there is one thing called adiabatic coefficient also, which is also a relation between Cp and Cv. Adiabatic coefficient, or it is also known as atomicity of gas. Okay, what is that? Gamma. And gamma is what? Cp by C. Gamma is Cp by Cv. Okay. Now, this is one relation. We know that. But other than that, can I do like this? N Cp delta T. That means I multiplied N delta T. Here also. What we can say? Heat added by change in internal energy. So gamma is also heat added by change in internal energy. This relation is also good. You should know, you should remember. Okay. Now I'm going back. Going back to slide number 10. Here it is. See the question. For a system like water that compresses on heating from 0 to 4 degrees centigrade, ratio of delta U by Q added is. So when you talk about water, he says that it is getting compressed when you are heating it from 0 to 4 degrees centigrade. That is anomalous expansion of water. When you heat it from 0 to 4, instead of expansion, it compresses. Okay. After 4 degrees centigrade, when you are heating, it expands normally. There is no problem. Below 0, it behaves normally. But from 0 to 4 only, it behaves in a different way. That's why it's called anomalous expansion. So 0 to 4, if you are adding, its volume in fact decreases, compresses. So that's what he says. For a system like water that compresses on heating from 0 to 4 degrees centigrade, ratio of delta U by Q added is. What will be delta U by Q added? Okay. Greater than 1, less than 1, equal to 1 or none. Okay, so what happens? Let's think. Okay. Heat you are adding. Okay, Q is added, so that the temperature can increase from 0 to 4. But what happened in that? Compression. When water compresses, water gets compressed. So when water gets compressed, that means work done is negative. Work done is not positive, remember that. So if we apply the first law, it says delta Q to delta U plus W. But unfortunately here, work done is negative. remember, delta Q, delta U, and this is minus. Why? Because it's compression. So delta U is what? Delta U became delta Q plus W. That means delta U is more than delta Q. Delta U is more than delta Q. Okay. Suppose you gave 5 joule of heat, then also inside also compression happened. Okay. So inside compression has happened. It means internal energy has increased more than what heat you have given. So what is our answer? Delta U by Q added is what? Delta U by Q added is greater than 1. Okay. It's greater than 1 in this case. Clear? Okay. Right. Let's see what this is now. For monoatomic gas. For monoatomic gas he is asking. So that means I should give you gamma. Let's discuss gamma for monoatomic, diatomic, polyatomic. Okay. The previous slide we will have. We have a little space on this. So we can discuss. Right. So gamma now. The gamma is Cp by Cv, we know. And we also know that Cp minus Cv equal to R. Now, as I said that this is true for all the processes. Okay, this will be same for all the processes. But gamma equal to Cp by Cv will be different for different processes, different gases, not processes. This is same for all the gases. This is different for different gases. Okay, so now monoatomic gas when we talk. What is the value of gamma? What is Cp value for, or rather Cv value for monoatomic gas? Cv value for monoatomic gas is 3 by 2R. We will see this in kinetic theory of gases. Okay, but we should remember that, right? So Cv for monoatomic, 3 by 2R. Okay, now this 3 by 2R, if I am going to keep over here, Cp value will come automatically. What is Cp value? 5 by 2R. Okay, Cp, this way I should write. For monoatomic, Cv 3 by 2R and Cp 5 by 2R. Okay, so gamma, Cp by Cv, that is 5 by 3, that is 1.66. Okay, diatomic, for diatomic Cv value is 5 by 2R and Cp value 7 by 2R. So gamma for diatomic 7 by 5. Okay, then for polyatomic, non-linear. Okay, polyatomic, non-linear. For polyatomic, Cv is 3R and Cp be 4R. Gamma for polyatomic then. So gamma for polyatomic is 4 by 3. So this is 1.66. Okay, this is 1.4 and this is 1.33. So which gas has least gamma value? Polyatomic. Maximum gamma value? Monoatomic. Okay, so this is gamma. Okay, now let's go back to the question that we were having. This is the question. For monoatomic gas at constant pressure, delta Q is 100, W equal to, in fact we have to find W, and delta U also we have to find. Constant pressure. Okay, let's understand what is happening. Delta Q you have given. Okay, so delta Q when we have given, delta U will increase and work will also be done, but he is asking all that and only delta Q is given. So what to do? Delta Q we can write as NCP delta T. Okay, let's assume n is 1. Otherwise, n also will be given. Okay, assuming n is 1. But if you don't assume also, there is no issue in that, no problem. N also will do. Okay. So, NCP delta T value given. Monoatomic gas is there, that means I know Cp value also. What is Cp value for that? 5 by 2R. So, N into 5 by 2R delta T. This is given to me. Then what he is asking? Delta U. Delta U is NCV delta T. Cv is 3 by 2 R. Delta T, can I find delta T from here? Yeah, why not? This 5, this is 20 I can do. So, delta T we can write as 40 by NR. So, 40 by NR. NR cancelled. 20, 60. Delta U is 60 here. Then W, this is 100, this is 60. So, W is 40. What is there in it? Simple. Done. Over. Okay. So, here we use what? NCP delta T, and from there only we could find. Okay. Right. Diatomic gas at constant pressure, delta U 15, find delta QW. So, for diatomic gas now. Okay, but this time delta U is given. Okay, whatever. Delta U is also we know NCV delta T only. Okay, delta U 15 and diatomic gas means Cv is 5 by 2R into delta T. This is first relation that we have. Okay, delta Q, now again this is at constant pressure. Okay, so delta Q will be NCP delta T then. So can we have N delta T value? We said yes, this is 5, 3 ja 15. Okay, so N delta T value is 6 by R. Okay, N delta T value is 6 by R and Cp value is what? Cp value for diatomic gas is 7 by 2R. R are cancelled, this is 3, so this is 21. 21 is the heat given, 15 is delta U, so W will be what? 6. Simple. W is 6 joule. We have done. Then what is next? Let's see. Okay. Ideal monoatomic gas. Delta Q is 20, delta T is 10 at constant pressure. Okay. So he is asking that for the same gas, how much should be delta Q, which is written as X, for the same change in temperature, 10 degrees centigrade at constant volume. Okay, how much heat is to be given at constant volume for the same change in temperature. Same thing that I was explaining you a little while ago, that at constant pressure more amount of heat is given as compared to isochoric process. So Mayer's relation, he is asking it. Okay, so at constant pressure process, delta Q is equal to NCP delta T equal to 20 joule. Okay, so Cp value you know it's monoatomic given. So find N into Cp value is 5 by 2R and even the temperature change is given 10. That's equal to 20. This is our first equation. Second is at constant volume. So at constant volume what amount of heat is required? NCV delta T is required. Do we know Cv? Yes, it's a monoatomic gas, so it is 3 by 2R. And delta T is 10. So, he is just asking us NR value. What is NR value from here? Okay, this is 5 4 ja. Then this is 2 5 ja. So, NR value from here is coming just 4 by 5. NR value is 4 by 5. Let's put in this one. So, NR, this is NR. NR value is 4 by 5. into 3 by 2 into 10. So this is 5 2s are 10. 2 and 2 gets cancelled. Answer is 12. So in constant volume process, for the same change in temperature, how much heat is to be given? 12. Whereas at constant pressure process, how much you have to give? 20. Reason is because here work is being done. How much? 8 joule. If suppose in this one it's asked that how much work is being done, then answer is 8. Okay, because change in internal energy is 12 joule in this process at constant pressure. Change in internal energy for the same change in temperature doesn't depend on the process. Okay. What is adiabatic elasticity of diatomic gas? Adiabatic elasticity. Okay. So adiabatic elasticity, what to do? Adiabatic elasticity means is, if you remember that bulk modulus is used for finding out elasticity of gases and liquids. And what is bulk modulus? Delta P minus delta V by V. And I should write it as minus dP by dV into V. Okay, so dP by dV means you have to differentiate pressure with respect to volume. So, elasticity for adiabatic process. The adiabatic process is what? P V to the power gamma is constant. This represents adiabatic process. So, if you are going to differentiate it, okay, if you differentiate it, beta value, that is what he is asking, elasticity. So, beta value will come out to be gamma P. Beta value will come out to be gamma P. And for isothermal process, if you are doing, for isothermal, beta value will come out to be P. Okay, so for adiabatic, gamma P, isothermal P. So if suppose it is asked that comparatively, which is more elastic, then you say adiabatic process is more elastic in nature as compared to isothermal process. Then the second question they will ask you, if suppose we are talking about PV graph, then whose slope is more? Whose slope is more? Adiabatic. Okay. Slope of PV graph for adiabatic process. For adiabatic process is more than slope of isothermal process. More than slope of isothermal process. Okay, you have to remember that. So yes, elasticity is more as well as slope is more for adiabatic. Okay. Alright. Now what this is? For triatomic gas at constant pressure, delta Q is 800 calories. What is W? Simple question. Only thing is, now this is triatomic, that means polyatomic gas. Alright. Delta Q given. Right. So delta Q is given to you as 800 calories. At constant pressure. Delta Q is given, that means this is NCP delta T because it's at constant pressure. Okay, and what the question is asking, W. Now what is W at constant pressure? And W is NR delta T. What is Cp value? We all know that Cp value for which gas? Triatomic gas is 4R. Okay, so N into 4R into delta T equal to 800 calories. Okay, so this is 200. So NR delta T is 200. That is what work done is. So 200 calories. That's all. Okay, so in this triatomic gas, we calculated work done as 200 calories if suppose delta Q is 800. So if he is asking delta U is 600 calories. Okay, delta U is 600 calories. Right. ideal gas equation and relation. Okay, fine. Ideal gas equation, we all know. PV equal to nRT. Okay, PV equal to nRT. N is number of moles. Okay, fine. Now, if you are going to talk about the processes, the different processes that we have, suppose we are talking about isochoric process. Isochoric process means it's a constant volume process. Constant volume. When we say it's constant volume, and immediately this volume is constant, that means P is proportional to nRT. nR is constant, remove that. P is proportional to T. P is proportional to T, or P T to the power minus 1 equal to constant. T we can brought it over here, this becomes constant here, so P by T is constant. This is isochoric process. Same way isobaric. We know that it's a constant pressure process. The constant pressure process is here. Pressure is constant. Now volume will be directly proportional to temperature. Okay. So V is proportional to temperature. So how we can write that as V T to the power minus 1 equal to constant. Okay. Then what more? More processes are there. Now what process? Constant volume we saw, constant pressure we saw, constant temperature. Isothermal process. So temperature is constant. That means this is constant. This N is also constant, R is also constant, T is also constant. Then PV is constant, it means, because this all is constant. Let's say PV is constant. Now PV is constant means P is inversely proportional to volume. P is inversely proportional to volume, that is our isothermal process. Then is adiabatic. It's adiabatic process. Now adiabatic process is PV to the power gamma. And gamma we have seen already. Atomicity you say, or you say it as adiabatic coefficient. Okay. So PV to the power gamma is constant for adiabatic process. But we can have more relations. Why? Because this relation, ideal gas, is applicable to all the processes. Okay, so PV to the power gamma is constant, fine, that is one relation. But now in place of P, can I write nRT by V also? Answer is yes, we can write. So in place of V, P, if I am writing nRT by V, nRT by V, V to the power gamma equal to constant. Okay, N is constant, R is also constant. So constant by constant will be what? Constant only. New constant but constant. So then this you take that side. What we have now? T V to the power gamma minus 1 equal to constant. Another relation. This is one relation. It's another relation. Okay, then one more thing I could have done. Here V I could have replaced. So in place of V, what I can write? nRT by P. Here. So new relation, one more relation will come. What is that? So P we don't want to change. V. In place of V I am writing nRT by P. And to the power is what? Gamma. Again N is constant, R is constant. Those go constant by something constant. Again a constant. So what is coming finally? Finally P is here. This P is to the power gamma. So we'll write P by P to the power gamma, T to the power gamma equal to constant. So what is the relation? P to the power 1 minus gamma, T to the power gamma equal to constant. This is third relation. Okay, so in adiabatic process we have three types of relation we can have. First for PV, second for TV, third for PT. So this way adiabatic process can be written in three ways. Okay, we should be able to identify, right? We should be able to identify them. Okay, fine. Let's do a question now then on that. What is the question? See, P is proportional to T square, then what is gamma? P is proportional to T square, then what is gamma? Now it is giving us relation in P and T. I can write this as what? P T to the power minus 2 equal to constant, right? Okay. Now P and T, what type of relation is there actually? Let's see. P and T, this is a relation. P to the power 1 minus gamma, T to the power gamma equal to constant. Okay. So P to the power 1 minus gamma, T to the power gamma equal to constant. Now what I can write this? I can write this as P T to the power gamma by 1 minus gamma equal to constant. What I did here, both sides, normally what we do, suppose that I have, suppose P square T cube. Now I took square root on both sides square root, P square T cube and constant square root. Okay, so what will happen here? Be P T to the power 3 by 2, and here constant square root, it will come on new constant, but it will be still constant. It will become P T to the power 3 by 2. Here also the same thing. Now here the power was 1 minus gamma. Like here power I have written is square 2. Here is 1 minus gamma, and in place of 3 here is gamma. So what I did now here I did square root. That means to the power 1 by 2. Here I did to the power 1 minus gamma. Okay. So this became P and this became gamma by 1 minus gamma. Exactly same. So now this is the relation for me. Now this and this I am going to compare. What I have then? Gamma by 1 minus gamma equal to what? Minus 2. Equal to minus 2. Okay. So what we have? Gamma equal to minus 2 plus 2 gamma. So gamma equal to 2. Okay. This is one way. But if suppose that this is, you are finding it tough, what to do? Any other process is there, or other ways? There. One more method is there. Okay, because there is a possibility that you don't remember. Okay, you don't remember that this relation. Then first you have to find this relation, and then we have to do this question. Instead, what we can do? Pt to the power minus 2 is there. Why not convert this into PV directly? Convert it into PV. So we already know that ideal gas equation is PV equal to nRT. And here is what given? T is here. So in place of T, what I can write? PV. PV by nR. nR is constant now. So in place of T, I can write PV. So put here P in place of T what? PV. PV to the power minus 2 equal to constant. So what we have? P into P to the power minus 2. V to the power minus 2 means it will come down. Do we require it down? No, we don't require. We require in the numerator on. So V to the power minus 2 equal to constant. So what we have now? P to the power minus 1, V to the power minus 2 equal to constant. So this is what? P V to the power 2 equal to constant. P V to the power 2 equal to constant. Okay. So we got the value of gamma. What is the value of gamma here? 2. Okay. We got the value of gamma as 2. So it depends on you, like you want to do it like this or you want to do it like this. It's entirely your wish. Okay. Just a moment. Yes, students. So gamma value is coming 2 here. Fine. Okay, let's move ahead. Gamma is 1.4, V2 is V by 32, P1. Okay. So that means adiabatic process only we are talking. Now, remember in adiabatic process and isothermal process, what is the difference, you know? The difference here is in isothermal process, if suppose I say that pressure is becoming double, suppose pressure is becoming double in isothermal, then volume becomes half, because ultimately PV is constant, no? So here initially, if the product is PV, then finally also product should be PV on isothermal. Okay, this is isothermal. So if pressure increases by 4 times, then volume will go down by 4 times. But in adiabatic, it's not like that. Okay, so if suppose in adiabatic, pressure becomes 2 times, then volume will be even more less than half. More less than half. Okay, so V final will be less than V by 2. Same way, if suppose volume is going down by or becoming half, then pressure will be more than double. In adiabatic process, it used to be more change. Changes used to be more. How here it was pressure double, volume half. Here pressure double means volume will be less than half. Understood? Adiabatic process, the changes are more, right? Where it will be used, just see. We'll see that. Okay. Okay. So gamma is 1.4, V2 is V by 32, P initial pressure is P, and what is final pressure? Okay. Now, if it was isothermal, volume is becoming V by 32, then pressure will become 32 times. Simple. But this is adiabatic. See that. Here itself, we will find it out. Okay. What is the relation? It's a PV to the power gamma equal to constant. That means P1, V1 to the power gamma equal to P2, P2 to the power gamma. Okay. So P1 by P2 or P2 by P1. P1 by P2 will do. P1 by P2 equal to V2 by V1 to the power gamma. Okay. So it's given to us that P1 is P, P2 we are finding, V2 value is V by 32, and this is V to the power gamma, which is 1.4. 1.4 means is which gas? Diatomic gas. 7 by 5 is its gamma value. So 1.4. Okay. Fine. So here is gamma. Gamma. V and V gets cancelled. What is P2? P2 is P into 32 to the power gamma. 32 to the power gamma. Normally, in isothermal process, it would have been P into 32 only, because volume has gone down by 32, pressure will increase by 32 times. But it is 32 to the power gamma, and gamma is more than 1. So what will happen? Pressure will be more than 32 P. Okay, this pressure is more than 32 P. Remember that. That's how adiabatic process is. Okay. All right. Okay, one more question is there. Let's see what the question is. Initial pressure and volume of the gases P and V. Isothermal process they are undergone. Volume has become 16 V. Then again adiabatic process, volume is again V. What is final pressure he is asking? Okay, it's easy basically. This is isothermal process, and what happens we all know, PV is constant. So if volume has become 16 times, then pressure has become what? 1 by 16. We know that. Right? Nothing new. Okay. Now adiabatic process. Okay. In adiabatic process, now we require one more thing, like which gas it is. Because unless we know the gamma, we can't find final pressure. So we can choose what type of gas it is. Shall we take monatomic? Take monatomic gas. Okay, it's a monatomic gas. Now what? PV to the power gamma finally. So P1, V1 to the power gamma, P2, V2 to the power gamma. So P1 is P by 16. Not like this we'll do. Okay, ratio we'll take and then we'll solve. Okay. What we have to find? Final pressure. That means P2. Okay, fine. So P1 by P2, V2 by V1 to the power gamma. Okay. P1 is what? P by 16. So P by 16 into P2. V2 is V and V1 is 16V to the power gamma. Okay. So what we have now? This V and V gets cancelled anyhow. So 16P2 equal to P into 16 to the power gamma. Now, if it's a monatomic gas, gamma will become 5 by 3. Okay. So P2 will come as P into 16 to the power 5 by 3 by 16. So 16 to the power 5 by 3, this is 16 to the power 1, 5 by 3 minus 1 will be 2 by 3. Okay. So P into 16. 16 means 4 square you can write if you want. Okay, but 16 into to the power 2 by 3. This will be the answer in terms of 4 or 2 also we can write our wish. Okay. So it will be 4 square, so 4 to the power 4 by 3 or 2 to the power 8 by 3. Okay. So we can write like this. This will be P2. Okay. Alright. Let's move ahead. One more question is there. More questions you are solving, more you will understand. Okay. So gamma is 1.5 at NTP. If gas is suddenly compressed at NTP to V by 9, T final. Okay, again adiabatic process only is there. And this time he want relation between V and T. Okay. So gamma value 1.5. That means it's not an ideal gas. There's something hypothetical gas maybe because 1.5 will never get it. Gamma for monatomic is 5 by 3, that is 1.66. Diatomic 7 by 5, that is 1.4. And polyatomic, gamma value 4 by 3, that is 1.33. Okay. So this is 1.5 means maybe some hypothetical gas. The gas is suddenly compressed to at NTP to V by 9. What is the final temperature? There is no problem. Okay. So again, same formula, but this time it is V and T relation. So do we have V and T relation? We do have PV to the power gamma equal to constant. This P we don't want. So in place of P, what I can write? T by V. V to the power gamma equal to constant. What is the relation? T V to the power gamma minus 1 equal to constant. Okay. So final temperature he is asking. Okay, we can do that. Okay. So let's put again relation we will do. What we can do? We can say T1 V1 to the power gamma minus 1 equal to T2 V2 to the power gamma minus 1. Okay. What is temperature? T final. So let's say initially temperature is T only. Later on we'll think about what is the temperature actually at NTP. So let this be T only. Okay, V1. V1 is V given to you to the power gamma minus 1. T2 we are finding and V2 has become V by 9. V and V gets cancelled here. So T2 is T into 9 to the power gamma minus 1. Okay, 9 to the power gamma minus 1. Okay, that's it. Gamma value is 1.5, we can keep it in that. 1.5 minus 1, that is 1 by 2, and this you can write 3 square. Okay, so T2 will be coming as 3T. Now whatever is the temperature, like you want to take normal temperature and pressure 0 degree centigrade, 273 Kelvin, you can keep it. So 273 into 3. If normal temperature and pressure, if you are taking a room temperature, I don't think room temperature we take, But if it's room temperature given, then we can say 300 Kelvin, 300 into 3 is 900. It depends on like what is given to us. Okay. Alright. Then, then now we should discuss about graphs. Okay. So graph means mainly we talk about PV graph. Basic graph. Like in 1D motion we talk about VT graph, velocity time graph. Okay. Same way here is PV graph. The PV graph area gives work done. Okay, PV graph area gives us work done, right? So if we talk about PV graph in general, PV graph. Okay, the PV graph we make for all the processes. And it is also necessary to understand the process, okay? The PV graph, we can understand the process in a better way. That is also there. Okay, so let's see then how work is calculated. Now suppose that I am taking one process like this. Two processes I will take, I will make it a little smaller. This is one and this is another one here. Okay, now in one process, this is clockwise and this is anti-clockwise. So here I have written area gives work done. I will just rectify that. Area under the curve, area under PV graph gives work done. Okay, now what this process I have shown you? I have shown you cyclic process. Suppose this is the initial position here, then it is returning back to the same position. This is cyclic process. This is also cyclic. Okay. Now we want to see the work done in that. Okay. So work done, for that work done, what I'll do is I'm just putting a line over here. Same line I'll be putting here also. Okay. So now what I'm trying to say you, I'll be talking about this. This is my process number 1 and this is my process number 2. Okay. So what is work done in process 1 and what is work done in process 2? That we have to see. So when you talk about process 1, okay, process 1, that means A to B. So when you talk about work done in AB, what you have written? Area under PV graph. Okay, understandable. Now what is area under PV graph here? That we have to see. So this and this. Okay, so this is PV graph. Area under means this is area under. This entire area is work done in process AB, that is W1. Area under AB arc. This arc is the area under that. So in this one it's very easy for me. What will be happening? This is a circle. Radius I can calculate. So this will be pi r square by 2 area and then this is a rectangle. I can find that. This is work done in AB. But then there is another process which is BA. In BA what will be work done? Now let me take it separately now. This is BA, right? So BA will take here. Okay. So only BA we are talking. We are not talking about the upper one. So this is B. This is A. This is the process. Now what is work done in this? Work done in this also is area under that. Area under that is what? This is area under that. Okay. So what is area? Under that means what? Under that means this. Okay, area under that means this. If I can make over here without disturbing this one. Okay, so work done W2, area under VAR. Okay, so in VA, this work is done, whereas in AB, this entire work is done. So what is the total work done in the process? W1 plus W2, two processes are there. Okay, so work done in this is equal to W1 plus W2. Okay, in the first process, what is happening? Volume is increasing. Here volume is less, here volume is more. And second one, volume is decreasing. That means this is expansion, this is compression. Expansion means positive work, compression means negative work. Okay, so from this entire area, you subtract this area. What is going to come? Area of the circle. Okay, area of the circle. So here work done in this case will be area within the graph. Okay, this is area within the graph. Answer is positive work done, negative work done. Say positive work done. Why? Because in this one, area under that is the upper one, upper curve, and upper curve is expansion. So upper curve is expansion means work done is positive, right? But in general, we make one rule. If it's a PV graph and the process is cyclic, okay, cyclic process, and the way in which you are moving is clockwise. In a cyclic process, if it's a clockwise process, clockwise motion is there, then work done is positive. Okay, convention we have. PV graph, clockwise motion, work done positive. Okay, anti-clockwise, work done will be negative. Because in this one, compression is above, expansion is below. In the PV graph, compression is above. So in compression, you will take entire area. Whereas when you talk about expansion, you will take just this below area. So work done will be area under the curve. But since the flow is anti-clockwise, we will say that work done is negative here. Okay, now in this one, how to calculate radius at times it is asked. Okay, so what will happen in this one? This pressure will be given. This pressure will be given. So this is diameter, P2 minus P1 will become diameter. Or this P1 is given and V2 is given. So V2 minus V1 is the diameter. So we can find out what the radius is. So in this case, what will be our work done? Pi P2 minus P1 by 2 into V2 minus V1 by 2. Sometimes radius is not given, they will give P1, P2 and V2 even only. So we have to write like this. Don't write as pi into P2 minus P1 by 2 whole square. Don't write like that because we have to justify units. So work done, so pressure into volume only is work done. Okay, so you have to write it like this. So this is how PV graph is used to calculate work done. Okay, now this we did. Now what more is there? Now suppose we are going to talk about various thermodynamic processes are there, right? Isothermal, constant pressure, constant volume, adiabatic. In which process more work is done for the same change in volume? Okay, let's see. Which thermodynamic process does more work for same change in volume? For same change in volume. Okay, that we have to see. So we have to make the graph. Okay, now we are saying same change in volume. Okay, this is pressure and this is volume, and same change in volume means I will make one more line over here, one more line or two more lines. Okay, this is for initial position. Initial position will be on this, and one more we will make for final. Okay, something like this, or we'll bring it closer. Okay, initial position is it? Our initial position is this. From here we have to start. Expansion, and what we are going to see is expansion. Work done by the gas. Which thermodynamic process does more work for same change? Yes, for expansion. Okay, so first we'll talk about constant pressure. Now constant volume I can't talk because I am saying expansion and constant volume work is not done. So constant volume is rejected, right? Okay, so okay, with this only should make. All right. So constant pressure, I mean constant pressure will be like this only. What else we can do in constant pressure, right? So constant pressure, constant pressure. Okay. Now what? Constant volume. Now suppose this is volume V and this is volume 2V. Let's assume, okay, volume is doubling. So what will happen if I am going to talk about isothermal process? If volume is doubling, pressure will become half, right? Okay, so let's make it like that only. I have to make it freehand only. Okay, so pressure, if this is pressure, then half pressure will be where? Here only, here somewhere. Okay, so let's join. This P by 2, and this is isothermal. Adiabatic, what we learned? We said that if volume is doubling, pressure will be less than half, right or not? More deeper. More change is there in adiabatic process. We discussed that, right? So what will happen? Maybe for that pressure will be somewhere here. So how will be this adiabatic? Like this. This is adiabatic. See that how easily we made it. So there is no confusion at all that which is going to be isothermal and which is going to be adiabatic. Right? This is isothermal, this is adiabatic. Now what the question was? Question was in which process we are doing more work. More work means area. In which process more area is there? Constant pressure, maximum work, then isothermal, then adiabatic. So in adiabatic, work done is least. Isobaric greater than isothermal greater than adiabatic. Compression also we can make from the same way. Compression also we can make. Why not? So for compression, okay, I'll just try and take this one. Not this. Okay. I'm not able to take Y. Forget it, I have to make it. So I'll make the graph one more time. Okay, so here's the graph. This is P, this is V, and this time what we have thought? We thought that we are going to compress it. So if we compress it, okay, compress it, then again we have to take two lines so that we can show the compression in proper way. Okay, starting point, maybe starting point is this. So constant pressure again, constant pressure is the easiest actually. The constant pressure will be like this. Straight line. Okay, let's frame it. Now what? Now I'll make isothermal. So what we want to do, suppose that volume here is 2V. Just in the previous case how we took, same way. Okay. This volume is 2V and this is V. So we are making it half. So when you're making it half means pressure will become double. Whatever is pressure here, same will be pressure here. Or rather, double will be pressure here. Okay, so isothermal. Slightly better I can make. Like this I will make, it is better. Okay. Okay, now if here pressure is P, I know that this is 2P in isothermal. But in adiabatic, pressure will become more. Okay, if volume is decreasing and becoming half, pressure in adiabatic will be more. So maybe somewhere here. Okay, this is adiabatic. This is isothermal. And last one I don't have to tell you, it's a constant pressure. So this is how we can make the graph very easily, or we can distinguish the graph between adiabatic, isothermal and isobaric process. Okay, same way if graph you want to make for different gases, monatomic, diatomic, polyatomic, for adiabatic process, how that is going to be? Okay, that also you'll see. That possibly will finish the class after that. Okay, so graph for different types of processes. Processes? No, different type of gases. For monoatomic, how will be the adiabatic graph? How will be the for diatomic? How it will be? For polyatomic, how it will be? Okay. Expansion only I am making. I am not making compression now. For expansion. Okay. Now we all know that gamma for monoatomic is 5/3. Gamma for diatomic is 7/5. And gamma for polyatomic is 4/3. Okay. Does it have any say as far as this is concerned? Obviously, no. More the gamma, more sharp will be the changes, more will be the change. So if suppose this is initial, okay, this is initial pressure and volume, whatever that is. Okay, suppose we are doubling it here. Okay, so whose gamma is more? 5/3. So in this one, change in pressure will be more. Where pressure change in pressure will be less? Polyatomic. So in this case, if I am going to make the graph, 3 graphs I will make. Okay, will be similar graphs. Okay, nothing much of a change. So now which one? This is mono. This is diatomic. This is poly. This is dia, and this is monoatomic. More will be the change in monoatomic because gamma of monoatomic is max. It is 1.66. This is 1.4, and this is 1.33. Gamma only decides how much more will be the change. When it was isothermal, we said that if volume is doubling, pressure will be half. Then gamma will become 1.33. So then it will be change in pressure will be more, but with what factor? 1.33 for monoatomic. Here 1.4, so even greater. 1.66, even more greater. So this is monoatomic, which shows more change in pressure. This is less change in pressure. Okay. So this is how we can identify poly, dia and monoatomic. This is it today. Okay. So first I'm sharing with you the QR code. Okay. Scan it so that whatever we have done in the class, you have it with you and you don't have to spend time in making the notes. Okay. Just a moment, it will come. Come on. It takes time maybe because it has to gather all the things, how many 24 slides are there. So it takes time. Okay. Scan it, you will be getting the notes. Okay. So this is it, students. That's all for today. Bye bye. Keep studying.